Page 2 of HL Addendum for Applications of Differential Calculus, number 27. Let's see, how far should x be from A for angle theta to be maximized? So they got this diagram here of, I don't know, some bars sticking out of a wall or something. It's similar to the problem we just did, except remember the last problem we had these two diagonals. Basically, we're trying to minimize the distances here. And in this case, what we're trying to do is we're trying to maximize this angle. Let's try to figure out if we can let's try to figure out if we can make a equation with this angle on the left side and, some ratio of these sides on the right side. So let's have the distance of x from A be like our principal variable, and we'll just call that small x. And if that's small x, then of course this distance here is 4 minus x, right? But now that we know expressions for those two sides, we could figure out expressions for this angle and this angle. And do you see how these two angles are important to maybe figure out the angle theta? Because like parallel lines cut by a transversal alternate interior angles congruent. So this would be equal to that one, and this would be equal to that one, right? So if we figure out a expression for the top angle and expression for the bottom angle, we can just add them up, right? Now, this would be a trig problem, right? Because if we want to figure out this angle, all we need to do is make a ratio between this side, and then we'd use tangent, right? Because opposite over adjacent. So let's call this alpha. We'll call this beta. So the angle alpha is equal to the inverse tangent of x divided by 5, because that would be opposite over adjacent. And beta would be equal to the inverse tangent of 4 minus x divided by 3. And then we just add those together. So we'd have angle theta is equal to inverse tangent x divided by 5 plus beta, which is inverse tangent 4 minus x divided by 3. Now, if this was a paper 2 problem, you could just type this into your calculator, and then you would get an expression which you could graph and just find the maximum point, and that would be, you would find the x value which makes this maximum, right? So, since maybe it's not a paper 2 problem, let's look at this formula which calculates the tangent of the sum of two angles. And I think we'll be able to use this because look, we have an angle alpha which has a known tangent, x over 5. We have an angle beta which has a known angle, which is 4 minus x divided by 3. We could just take x divided by 5 and 4 minus x divided by 3 and plug them in. Every time we see tangent alpha, tangent beta, we plug it in. And then we can get an expression for tangent of alpha plus beta, which actually is tangent of theta. So let's do that. So we have tangent of theta, which is actually equal to alpha plus beta. And then we'll say, okay, tangent of alpha, x divided by 5, plus tangent of beta, 4 minus x divided by 3, divided by 1 minus the tangent of alpha, x divided by 4, 4 minus x divided by 3. So then if we take the inverse and tangent of that, we're going to have like probably an expression that maybe we can figure out what the x value is maybe without the calculator, or without a graphing calculator at least, okay? So let's see. Let's try to algebraically simplify this. We can multiply everything times 5 times 3, 5 and 3, so that we can get those out of the denominator. So we'll get 3x plus 5, 4 minus x on top, and on the bottom we would have 15 minus 4x plus x squared. No, minus x squared. Minus x squared. Okay, and then if we want to, okay, and then we can distribute the negative sign if we want to. Let's simplify this even more. 3x plus 20 minus 5x over x squared minus 4x plus 15. So on the top, we basically have negative 2x plus 20. So now we have an expression with which we have tangent theta on the left and this terrible polynomial on the right, and we're going to take the derivative of both sides so that we can figure out when the derivative is 0. The derivative of tangent theta is secant squared, and we're just going to do implicit differentiation here because then we don't have to like take the derivative of arctangent. So we get that, right, for the left side. And the right side is going to be quotient rule. That's going to be horrible. X squared minus 4x plus 15, oops, squared, and on the top left, x squared minus 4x plus 15 times the derivative of the top. The derivative would be negative 2. Subtract the top, which is negative 2x plus 20, and then we'll take the derivative of the bottom, which would be 2x minus 4. Okay, and now we would need to expand the top, so see if we can expand or combine any, what do you call it, like terms. Negative 2x squared plus 8x plus, or minus 30. And then, like here, we would have plus 4x squared plus 4x squared. The middle term would be 40x and 8x, which would be 48x minus 48x. 20 times minus 4 is negative 80 plus 80. Okay, and the bottom would be what it was before. Now let's try to simplify the top a little bit. So, for example, negative 2x squared, 4x squared, so that'll become 2x squared. 8x minus 48x, that would be minus 40x. And negative 30 plus 80 would be plus 50. And the bottom would still be x squared minus 4x plus 15 squared. And that is equal to secant squared theta d theta dx. I am going to rearrange that. I'm going to divide the secant squared theta over here to the bottom. And now I got this d theta dx. And now I can, secant squared is actually 1 over cosine squared. So instead of writing secant squared on the bottom, I could write cosine squared on top. Cosine squared theta on top. And d theta dx, we're going to set it equal to 0 so we can find the minimum or maximum value for this expression. And, okay, looking at this, what would make this expression 0? Well, one of the things that could make it 0 would be the cosine value. The cosine value could be either, the cosine value would be 0 that we want, but what values of theta make cosine 0? Basically, that would be pi over 2 and 3/2 pi, right? Yeah, those are the two values that make cosine 0. Is there anything that makes 2x squared minus 40x plus 50 0? Remember how I said that maybe we'll get this to the point where you could at least do it with a regular calculator, not a graphing calculator. So here we are. Now, you could do this by hand. You could figure out the root to 2x squared minus 40x plus 50 by using quadratic formula, right? But I'm just going to show you using poly-SMLT, polyroot finder, order 2, next, and we're going to put 2, negative 40, and 50. 2, negative 40, and 50. Enter. Solve. Oh, and it gives us these horrible numbers here. So that's what you would get if you would do quadratic formula, which is why we didn't do it. Okay, and then so just to get some decimals here, we have 18.66 and 1.34. Let's see, we're going to write both of those down. And then we'll analyze them to see which ones are actually good numbers. Okay, so x equals 18.7 or 1.34. Okay, and let's look at the picture again and see what that corresponds to. 1.34 would mean that this distance here, x, is 1.34 out of 4. That seems reasonable. 18.7 obviously doesn't work because then ax would be longer than 4 and the picture would make no sense. So we know that 18.4 is wrong. Now what about the answers we have for theta here? Theta equals pi over 2. From the picture it doesn't look like that's possible. I mean, how could you have an angle theta that was bigger than 90 degrees? No, that's not going to happen either. So none of the angles are helpful here. Only 1.34 meters is a possible answer. Okay. Now, as far as like figuring out if this is a maximum or a minimum, this one is not so bad. You could do a sign diagram. You would have 1.34 in the middle. You could put in like x equals 0, and you would get a positive number. I'm sorry, and x equals 0 makes no sense, or no, x equals 0 is okay. But x equals 0, and you would get a positive number here, right? And then the cosine squared value would be it would be an acute angle still, so it would be a positive number. And then the bottom number, 0 plus 15 squared, that would also be positive. So it would be positive. So if you were doing the sign diagram for the derivative of theta, then you would get positive left of 1.34. And then if you put a bigger number than 1.34, like for example, maybe 2, if you put 2 in here, then you could see that then you would get a negative number on the top and a, let's see, still a positive number on the bottom, okay, and still an acute angle, so that would be a negative number. So then you could see from the first derivative that basically you're going up, and then you get to 1.34, and then you go back down again, so 1.34 would be a maximum, okay? So that's it for 27. Let's move on to 29. Sonia approaches a painting which has its bottom edge 2 meters above eye level and its top edge 3 meters above eye level. So the painting is this green thing here. Given alpha and theta as shown in the diagram, find tangent alpha and tangent alpha plus theta. Okay. So tangent of alpha is relatively easy, right? Tangent of alpha would be opposite over adjacent. It would be 2 over x. Then it asks us to find tangent of alpha plus theta. Tangent of alpha plus theta. So that would be 2 plus 1 for the opposite and x for the adjacent. Now for the next part, they want us to find an expression for theta with just x in it, and they told us as a hint that theta is equal to alpha plus theta minus alpha. So what would be an expression for alpha plus theta? It would be inverse tangent of 3 over x, right? So we could say theta equals inverse tangent of 3 over x. And what would be an expression for alpha? Alpha would be inverse tangent of 2 over x. So there you go. We have a expression for theta in terms of x only. Part C, it says show that the derivative of theta with respect to x equals this thing here, and hence find x when d theta dx equals 0. So let's do that. So we'll take the derivative of this expression here with respect to x. The derivative of inverse tangent is 1 over 1 plus x, and in this case we have 3 over x as our angle, so it would be 1 plus 1 over 3 over x squared, and then we would do chain rule on 3 over x, so we would get negative 3x to the negative 2. And then for tangent, inverse tangent 2 over x, it would look pretty similar. 1 over 1 plus 2 over x squared, which is the derivative of inverse tangent. And then we get negative 2, or 2 times negative 2, no, 2 times negative 2 times x to the negative 2. Okay. And then we can like multiply both the top and the bottom by x squared so that we can get all the x squareds out of the denominators of the denominators. So let's multiply everything by x squared on the top and bottom. So that would give us negative 3 on top. It would give us 1, or it gives x squared plus 9 for this one, and for the other one it would be negative 2 on top, and then it would be 1, or x squared plus 4 on the bottom. Okay, and that's what we were looking for. Yeah, it was. That's exactly what we were looking for, right? All right, and find x when d theta dx equals 0. So if we set this equal to 0, then we would try to figure this out as much as possible without the calculator. If you look at this, you can say, okay, I am going to multiply the top by the denominators to make a common denominator. So I'm going to multiply negative 3 by x squared plus 4. I'm going to multiply positive 2 by x squared plus 9. I'm going to multiply the and then the right side I multiply by both 2, and it's just 0, so it stays 0. Okay, and now we can expand. Negative 3x squared minus 12 plus 2x squared plus 18. So that would be negative x squared plus 6 equals 0. So 6 equals x squared. X equals square root of 6. Okay. So we could do a sign diagram to make sure that x equals square root of 6 would be a maximum or a minimum. So square root of 6 in the middle of the sign diagram. Square root of 6 is about 2.5 or something like that. So if we put like 0 or 2 in for the expression here, 0 or 2. If we put 0 in there, we'd have negative 3/9 plus 2/4. So negative 3/9 is negative 1/3. Plus 2/4 is 1/2. So the positive number 1/2 is slightly bigger than the negative 1/3 here. So we know that to the left of square root of 6, we would have a positive slope. If we put a number bigger than square root of 6, then let's put in like 100 or something. If you put 100 in for x here and 100 in for x here, the denominators get to be about the same size. Then you just compare the numerators. So the plus 2 here is going to be slightly smaller than the minus 3 here, so the negative is going to win. So the right side is going to be negative. So basically you have positive slope and then negative slope. So square root of 6, x equals square root of 6 would be the maximum point. So the square root of 6 is a maximum, would give the maximum value. Interpret the result you have found in C. Well, if you put x equals square root of 6 here, that would maximize the viewing angle of the painting. Okay? All right. And last one, number 31. A, B, C are computers which are networked to a printer P. Where should P be located so that the total cable length AP plus BP plus CP is a minimum? So we got this, we got this, we got this. How do we minimize the total lengths? Oh, there, yeah, and there's no N over P does not exist, right? A over P. Oh, A over P, yeah, A over P, B over P, BP, and CP. NP doesn't matter. Okay, so so where are they going to put P? And P must be along the distance AN or not? It doesn't seem like it, right? So yeah, it's not. It doesn't really say in the problem whether or not you can move P to the left and the right to make the cable length smaller. The answer in the back of the book assumes that P is along the line AN, but it never says that here. But you know, just to make things a little bit easier for us, we'll assume that. Okay, so we will assign a length X, maybe for AP. Okay, so, and then the rest of the distances we'll figure out based on X. So if this is X, then Pn would be 8 minus X, right? 8 minus X. And then we can figure out BP using Pythagorean's theorem, right? It would be square root of 4 squared plus 8 minus X squared. And then PC would also be similar. It would be 5 squared plus 8 minus X squared. And then so we would add that distance, the two square root expressions plus X. That would give us the total distance. And then basically we're going to try to minimize that distance, right? So let's write that out. So the distance, or the cable length, would be X plus square root of 16. And I guess we should maybe multiply everything out. 64. You know what? This is going to be awful. So I'm going to do the opposite. And then I think you'll see why I'm going to do the opposite. I'm going to put X here, and this will be 8 minus X, because you saw why, right? I was about to expand that, and it would have been awful, so sometimes we decide to do things in a problem, and then we see that we made the wrong choice, and so we got distance 8 minus X, and then we have square root of 16 plus X squared, and we have the square root of 25 plus X squared. And then we need to take the derivative of that to find when this quantity would be minimum. So it would be -1 plus 16 plus X squared to the, this is to the 1/2, so it would be, you take the derivative, you put 1/2 here, you put -1/2 here, chain rule 2x, same thing here, 1/2, 25 plus X squared to the -1/2, 2x, and then so we have 1/2 and 2 cancel, 1/2 and 2 cancel, so we have -1 plus X 16 plus X squared to the -1/2 plus X 25 plus X squared to the -1/2. Okay, and then we want to know when this is equal to 0. So, in hopes that we might be able to solve this without using a graphing calculator, let's try to 16 plus x squared to the 1/2 plus x over 25 plus x squared to the 1/2 equals 0. And now let's multiply everything by the denominators to try to get an expression with no fractions in it. So we would have negative 16 plus x squared to the 1/2 times 25 plus x squared to the 1/2 plus x times 25 plus x squared to the 1/2 plus x times 16 plus x squared to the 1/2 equals 0. Okay, now looking at this, this doesn't look like something that we would ever be able to find the root for, right? We can't square stuff because if we square it, it would just make like this huge polynomial, and it would still have, you know, if we did like a FOIL on this, we would just have like a bunch of little terms that have roots in it still. So this is pretty hopeless. So that's why we have the graphing calculator in paper 2, right? So I'm assuming this is like a paper 2 problem. We are going to, and like we cannot put this in poly root finder because it's not a polynomial, right? So let's go to y equals. Let's get out of this second quit. Y equals, and then we're going to put this into the calculator. I'm just going to put in the first term with you because maybe you haven't put something in this complicated before. Oops. X squared to the 1/2. Okay, and then I multiply that times 25 plus x squared to the 1/2. And actually, since they're both inside the root function, we could just put both in the root function as long as we put it in a parentheses. So here I'm going to put second insert left parentheses, and then here I'm going to put second insert right parentheses, left parentheses again, 25 plus x squared, 25 plus x squared, close parentheses, okay, to the 1/2. And then plus, and now I'm going to do all these, but I'm going to pause the video so you don't have to watch me do all that boring stuff, but I'm going to put this in, I'm going to put this in, and then we're going to see when it's equal to 0. Okay, I typed everything in. Now we can graph it. Okay, and then when we graph it, I did some zooming so you can see it well. You can see that the derivative function goes through the x-axis at this point. That is exactly where the real function, the original function, is going to have its minimum or maximum. Let's see exactly where that point is by doing second calc 0. And so the left boundary would be here. The right boundary would be on the right side here. So that would give us 2.58. So our x value of 2.58 would either be a minimum or a maximum. And we would do a sign diagram maybe to see if it is a minimum or maximum. We could put in a number to the left of 2.58 first. And actually, if you look at the graph, to the left of 2.58, we have negative values. To the right of 2.58, we have positive values. So we know it's negative, positive like that. So that means 2.58 is a minimum and not a maximum. And so basically, if that length there is 2.58, then the cable lengths AP, BP, and PC total are minimized. Okay. Now this problem could be done in a math studies way. The math studies way of doing the problem would be, instead of putting the derivative function in here, you would just put in the original function in here, and you would do second calc max or second calc min and find where the minimum point is. Okay. Now how would they try to force you to do it the Math HL way? Well, in the exam, they would force you to do the first derivative and interpret it and things like that. So even if you sneakily find the 0.2, 0.58 by using the math studies method, you're going to have to go through the first derivative anyway. So they'll do things to try to force you to use the more advanced methods. Okay, but if you're wondering why the heck are we using the derivative in this problem, it's just for practice. Okay, yeah, any problem can be done with the computer or the calculator, and that's what math studies says. Okay, so let's go to page 3.